All right, let's get started with segment relationships in circles, section 10.6. All right, in this section, we're going to have one objective: use segments of chords, tangents, and secants. So our essential question: what relationships exist among the segments formed by two intersecting chords or among segments of two secants that intersect outside a circle? All right, here's our first theorem, our segments of chords theorems. It states if two chords intersect in the interior of a circle, then the product of the lengths of the segments of one chord is equal to the product of the lengths of the segments of the other chord. So here we have chord AB and chord DC intersecting each other at point E. Something to note here is point E is not at the center. Earlier in our unit, we had a situation where the chords would intersect at the center, which is a completely different situation, resulting in different relationships. Here, we just have chords somewhere in the circles intersecting each other, and the intersection is not the center. So what this theorem is all about is it's saying each of the parts of the single segment, so AE's part times EB part, will equal DE times EC. So you take each of the two parts, multiply them together from the chords, and set those products equal to each other. All right, let's see this theorem in action. We're going to use the theorem to find the length of ML and the length of JK, so that's each of our chords. All right, these two chords intersect at point N, not at the center. N is not at the center. So we're going to set up equations to where this little chunk times this chunk will equal this chunk times this chunk. So let's see what our equations will look like. So we would say NK times NJ equals NL times NM. Substitution. That means we have x times x plus 4 equals x plus 1 times x plus 2. Do your distribution. So on the left side, we will have a single distribution. So x times x, and then that gets you x squared, and then x times 4, which is 4x. On the right side, we'll have x times x, which is x squared, x times 2, which is 2x, oops, and then 1 times x, whoops, it should not be a 3, it should be a 1, so just kind of cross that out, and then 1 times 2, which is 2. And then combine like terms. Getting us 4x equals 3x plus 2. The x squareds will zero each other out. So we can cross those out because they'll zero each other out when you subtract them from either side. Then combine the 3x with the 4x, resulting in x equals 2. All right, next you would substitute in to find the lengths of each chord. So ML is the x plus 2 plus the x plus 1. 2 goes in place of all the x's, resulting in a 2 plus 2 plus 2 plus 1, resulting in 7. So the length of ML is 7. And then for JK, substitute 2 in for your x's, so you get 2 plus 2 plus 4, which is a result of 8. All right, so our core concepts are, we've got these vocabulary words here. We've got a tangent segment. It's a segment that is tangent to a circle at an endpoint. Our example is the P to S, which is a tangent segment in blue here. And then a secant segment, which is a segment containing a chord of a circle and has exactly one endpoint outside the circle. So we have P to R, the full length is a secant. Remember, a secant intersects a circle twice, in this case at point Q and point R. So part of the secant is on the exterior and part of it is the chord inside the circle. So the external secant segment, which is the part of the secant that is outside the circle, in this example it's from P to Q. And the reason we need to talk about this vocabulary is so that we can talk about our next theorem. If two secant segments share the same endpoint outside a circle, then the product of the lengths of one secant segment and its external segment equals the product of the lengths of the other secant segment and its external segment. So there's lots of these vocabulary words that we just wrote down within this theorem. In short, if you have two secants with a common endpoint outside the circle, this implies that the external piece 1 times secant piece 1 equals external 2 times secant 2. So remember, your external piece is right out here, and then the full length of the secant would be from E to B. And then your external for the second secant is out here, and then the full length is from E to D. So when you multiply those two parts for each secant, set them equal to each other, that's the equation you would set up. So think of external times secant equals external times secant. All right, so let's see this theorem in action. We have two secants here. So we want to take the external portion. So we want to set up the length of RP times the length of RQ equals the length of RS times the length of RT. So the external piece times the full length equals external piece times full length. So substitute all the information that you have for your labels. So 9 times 11 plus 9, because you're doing the full length of the secant, so you want to add the 11 plus the 9. And then for the other secant, you want the 10, which is your external, times the full, which would be 10 plus x. And then do all your arithmetic, combining like terms, distribution, resulting in x equaling 8. Alright, so our next theorem states that if a secant segment and a tangent segment share an endpoint outside a circle, then the product of the lengths of the secant segment and its external segment equals the square of the length of the tangent segment. So this is a little bit of the secant has the same sort of setup as the previous theorem that had the two secants. But when you're dealing with a tangent and a secant, the tangent is the one that gets squared. So in this particular scenario, the length from E to A would get squared because that's your tangent, and set it equal to the product of the external, so from E to C, times the full secant, which would be from E to D. So the tangent squared equals the external times the secant. Alright, so let's take a look at this example where we can see this theorem in action. So let's start by setting up our equation. So we would set up our tangent squared, so RQ squared equal to the external RS times the entire secant RT. Substitute, so you have 16 squared equals x times x plus 8, resulting in 256 equals x squared plus 8x, because you would distribute here the x times the x, and then the x times the 8. Now we're dealing with a quadratic, so that means we need everything on the same side. So think through all your possible factors. That'll get you 256, and also add up to 8. So it's challenging to have a negative product and a positive sum. I don't think there's a possible combination here. So this is where for the first time we're having to solve this quadratic using a different method than factoring. So let's reintroduce ourselves to the quadratic formula. The formula x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. This is a formula we can use to solve any quadratic. And you would identify your a value, your b value, and your c value and plug them into the formula to find out what x is. So let's plug in our numbers into our formula. Then do your arithmetic. step by step, resulting in x equaling -4 plus and minus 4 square root of 17 by the time you simplify all of the radical. Now on this step here, make sure when you're dividing by a 2 here, and you've simplified down to, you simplify your radical, and so you result in 8 square root of 17. So this 2 has to go into both the -8 and this 8. And if it goes into both those numbers evenly, then you can continue to go to this last step where you get -4 plus and minus 4 square root of 17. Now because we have a positive and a negative, it's two different x values. We want to use the positive solution because the lengths cannot be negative. So we would eliminate the negative option and just identify that x is -4 plus 4 square root of 17. So when you type it in your calculator, it comes out to 12.492. So the length from R to S is 12.492. All right, and then our last example, finding the radius of a circle. Here we have an aquarium tank, and it looks like we have a chord DE, that is our diameter, and then connecting to the external piece, which is from E to C. So we have a secant from D to C and a tangent from B to C. So because we have a tangent and a secant, we would square the tangent, so CB squared equals, and then the external piece, which is CE, times the the entire secant, which is from C to D. Substitute, so we have 20 squared equals 8 times the 2r plus 8. And then 8 times the 2r, and then 8 times the 8 when we distribute. Continue to combine like terms. We get 400 equals 16r plus 64, resulting in r equaling 21. So our radius is r equals 21. So that makes our radius of the tank 21 feet. Since we're dealing with a real world scenario, make sure you include your units. And that's all for this section. And here's a little trivia for you. All right, see you in class.